Okay, hello everyone. Welcome to the lecture, and please confirm that you can hear me clearly and see my screen. Thank you for the confirmation. Okay, so what we were talking about last time. Um, Last time we talked about assembly language directives, and also we had a look at an example program, right? Where we first wrote our assembly language program in one file, and in that file we use the directives to define symbols and set their scope, which basically mean we using those directives, like for example dot equate, we define the symbols, and we set aside the memory, and then by using dot common and dot global, we made those symbols visible in the other file. In the other file, which was written in C, we first specified for the assembler that these symbols are defined in another file by using extern, if you remember, extern keyword. And then we defined a uh, function which was reading a 2 byte data, and then we were processing that 2 byte data using the program written is in assembly, but that program or that function written in assembly was actually called from the C file. Is everyone with me on that? Like this recap which I tried to give, everyone understands, or I mean your memory is refreshed to recall what we did, right? Okay, thank you. So now we will today we will talk about something about what is like proper register usage, and after that we will have a look at conceptual level. We have a look at how instructions are processed, and then what is the difference between a RISC processor and a CISC processor. Okay. So remember, we said like there are 32 general purpose registers available in ATmega 328P microcontroller, right? So, but when we are using those registers, we need to pay attention to some points. First is that R0 register, it is freely available. Freely available mean that you can put any data in this. However, you need to be careful when you are using the multiplication instruction. Later, when we'll see in our lecture, you will learn that when you multiply two numbers and both numbers are 8-bit, the result can be as long as 16-bit, right? So what happened that multiplication, when you multiply two numbers, the lower 8 bits of the result, they are saved in R0, and the higher 8 bits of the result are saved in R1, right? So if you are using multiplication, then in your program multiplication instruction, then you need to be careful with the usage of R0 register, because for example, if you do the multiplication and after that you do an instruction which overrides the content of R0, then result of your multiplication will be lost. So other than that, you are free to put any value in R0, but just you need to be careful when you are using multiplication. The other register, R1. Remember, just I said, like if you are doing multiplication, the higher 8-bit of the 16-bit result of multiplication is placed in R1 register. So you need to be careful for that part. And another thing is that R1 register always holds 0. So its content is by default 0. It is hardwired to contain the value of 0. So if you are using it, you must clear it after using, which means you need to reset back it to 0. Okay. So if you don't write anything R1, by default, when you power up your microcontroller, R1 will have a by default value of 0. And if you are like using it, then just make sure that you write back 0 to it once you are done with using that R1 register. Registers R2 to R17 and register R28 and R29. They must be saved and restored by caller. What does it mean? So what do I mean by caller? So remember, if you have done programming in a higher level language, you write functions, right? Let's say you have two functions. One is function, I'm just naming it as function one, right? For example, it can be your main program or main function, and you have another function, F2, right? So let's say in the body of F1, if you are making a call to F2, you will have here a statement, right? Like F2. So what will happen? Now F1 is caller and F2 is the Callee function, right? Now, when we are writing programs in assembly language, so we need to be careful about some things which we don't care about when we are writing programs in higher level languages. Why? Because their compiler is taking care of many things for us, right? But here we are don't have compiler. At most we have assembler, right? So that's why when function F1 is calling function F2, and here we are saying F1 is caller and F2 is Callee. So it is the job of the caller function F1 in our example to save and restore these registers. What does it mean? It means like before making a function call to F1, here are some instructions, right? If any of these instructions is using any of these registers, R2 to R17 and R28 to R29, right? So we need to be careful. Why? Because it is possible that you are calling in F2 and F2 is maybe also using one of these registers, right? So it will overwrite the values of these registers, and we don't want to do that. So what the caller need to do before making a function call to F2, it needs to save any of these registers it is using in this part of the program before calling the F2. If there is any part of the program before F2 which is using registers R2 to R17 and R20 and 8 or R29, and which are expected to be used after returning back from the call in this part, right? So we don't want the value of those registers to be overwritten. So it is job of the F1 that before making the function call, store all of these values of any of these registers in the memory, and then when it comes back, those values need to be restored from the memory and placed in the respective registers. So they must be saved and restored by the caller, right? Another information is that R29 and R28, remember all of these registers are 8-bit, right? However, when you combine, we can like logically, not physically, logically, the register R20 and R29, collectively, they are referred as register Y. Okay. And why? Why we are like naming them collectively as register Y? Because register Y is then used to hold an address, and addresses are 16-bit. So we cannot hold the address of a memory in a 8-bit register. So what we do is that we hold the or we place the 16-bit address of a memory location in two registers. Lower 8 bits go to R28, higher 8 bits go to R29, and collectively we name them as Y. And if a register is holding the address of a memory location, it's mean that that register is acting as a pointer to a memory location, right? So if Y has any 16-bit value and that value is a location in memory, right? Say the content of these two registers together, I don't know. Let me give you some concrete value. F0, I'm writing in hex definitely, AB. So then, and this is that address. So Y is pointing to this particular memory location. So Y is a pointer to this memory location. Okay. So that is Y is also known as a pointer register. Okay. Registers R18 to R27 and R30 and R31. They must be saved and restored by Callee. Okay. So which mean that if function F2, you are the right person who is writing the code of all these functions, right? F1, F2. So if you know that when you are writing the code of F2, you know that you are going to use any of these registers in the body of the function, right? So first you need to do what? That before actually performing the job or the operation of the function 2, you will have here a part of the code which will be responsible for storing any of the registers which you are using in the body, right? And once you are done with the function that need to be performed or operation that need to be performed by that function, you need to restore the values of those registers from memory back into those registers, right? And again, in our example, F2 is the Callee, right? In addition to that, Registers R26 and R27 collectively are known as, together they are known as register X, and R30 and R31, they are collectively known as Z, and their job is also the same, to serve as a pointer to a memory location. So in X, Y, and Z, you can store the address of memory locations or memory addresses, and then you can use them as pointers, which means that they point to locations in memory. Okay. Any questions? Any confusion about anything? Okay, so later we will basically have programs which will be using register Y and X and Z, but later when we like, I don't know, maybe couple of weeks later. But at this point, only this amount of information is enough for you to know that X, Y, and Z are basically, X is also like a collective name of R26 and R27, Y is R28, R29, Z is R30 and R31, and all of them can be used to hold memory addresses. Okay, now here we are going to have a look at how a program is executed, right? We have already seen in one of previous lecture an animation where we saw that how a program is executed, right? But here we will be not focusing more on like details, like for example, how the address is placed in program counter, and then how that address is issued to the memory bus, and then that instruction is read from the memory and so on. Like we are little bit at we will have the animation, but at a little bit higher level, not in not covering too much details, right? So initially your, okay, before even I go there, so here on the right side you have the program written in assembly language. So you have here bunch of instructions, right? So load immediate, add, load immediate, add, and sts instruction, store in static memory. And then you have a jump instruction. We have not yet covered jump instruction, but uh, let's put it in our program here. So we will see how jump works later on. Okay. And in this figure here, what you have is basically the code, the code of each instruction written in hexadecimal form in this column, second column, and in the first column you have the memory address where that instruction is stored, or code of that instruction code. Basically, that instruction is stored, right? So this is like content of your program memory, right? And from the program memory, you read the instructions, right? So initially your program counter points to 0. So the first instruction is read, right? And then it is decoded and executed. Then after that, the second PC is incremented to 1. Next instruction, which is E314, is fetched in and decoded and executed and so on. So basically you go through all the instructions one by one, right? Assuming there are no branches. So like we have sequential flow of execution, right? So we, like, our PC starts from 0 and now we are at 6. Then next will be the PC 7. Then the next will be PC 8. Then next will be PC 9, and the final will be PCA. And PCA is basically saying jump here. Basic jump here means that execute the next instruction which is available at the label here. So what is the label? The label is at the same instruction. So basically it is an infinite loop. So you are just saying keep executing this instruction and again and again. So jump here. Here mean go to the instruction which is pointed by the label here. Which is that instruction? This instruction. So then, okay, execute jump here, which means again this one, and so on. So it is an infinite loop. Okay. So, but here our focus is not on how jump instruction works. Our focus is on highlighting the fact that a program is executed in sequential fashion as long as there is no branch or conditional jump. Okay. So the PC, the value of PC moved from 0 to A, right? Okay. So in old architectures, what happened that, like, we are here on the left side, we are just trying to make this figure on the right more abstract. So here we are saying, okay, we have a processor, and that processor has two stages. First stage is fetch, where an instruction is fetched and then the instruction is executed. So in old architectures, what we were doing is, and again we have here the program as a combination of or as a collection of instructions. So in our architecture, what we were doing was that each instruction was first fetched and executed, and once it leaves the execution, its execution is completed, then next instruction, instruction 2 is fetched and executed, right? And once its execution is completed, then instruction 3 is fetched and executed, and so on, right? So which basically mean that at any given time, processor is working only at a one only on one instruction at any given time. But this is like kind of wastage of resources. Why? Because, for example, when instruction 3 is being decoded, our fetch stage is empty. So we are wasting the fetch stage, right? So we can basically improve the performance, which basically mean we can quickly execute the program if we don't waste the resources. So when the instruction 3 is in decode stage, we can bring in the instruction 4 in the fetch stage, right? So this is known as pipelining, and this is shown in the next slide here. So now we have exactly the same figure, but now we are executing the program using pipeline processor. So your first instruction enters the fetch stage, and in the next clock cycle, instruction 1 moves to the decode stage, and instruction 2 enters the fetch stage. In next cycle, instruction 1 is like completed, and then instruction 2 moves to the decode stage, and instruction 3 enters the fetch stage, and then next cycle instruction 2 is completed, instruction 3 moves to the decode stage, and instruction 4 enters the fetch stage, and so on, right? So now since we are overlapping the execution of the instructions, overlapping mean that when one instruction is in the decode stage, we have another instruction in the fetch stage. So we can be, if since we are overlapping, it's mean we can speed up the execution of our program, right? Now, this is a very simple example. Simple example in the sense that our pipeline has only two stages, fetch and what was that? Yeah, fetch and execute, right? But in real processors, it is not the case. At least you have like 4 or 5 stages, like very simplistic processors. And those which are advanced, they have even more number of stages. So the typical stages which are like, the processors which are like, used for learning purposes in labs, they have like fetch, decode, execute, write back, and memory stage or commit stage. Okay, so like 5 stages. So more stages you have, it's mean in the, for example, here at any given time we can have two instructions at the same time in the processor. Why? Because we have 2 stages. But if you have 5 stages, it's mean you can have 5 different instructions in the process in different stages of the pipeline at the same time, which mean that you are overlapping the execution of 5 instructions. So which mean that you can get theoretically more speed up, right? More the stage number of stage, higher the number of stages, higher is the speed up theoretically, right? But definitely there are like some practical limitations, because of which, for example, if you keep your make your deep pipeline super deep, too deep, it will you will start seeing the diminishing performance, which means yes, you will still have some improvement, but the amount of improvement you will see will not be that much significant. Okay, any questions here? No? Okay. So now the question is that how can we speed up the CPU? One, like we have like uh, looked at a concept of pipelining in a very simplistic way. So pipelining is one way how to speed up the CPU. Uh, but wait a minute, yeah. So even before, like other than the pipelining, one way to increase the speed of the CPU or to increase the performance of your CPU is like you increase the clock frequency. What do I mean by clock frequency? So here, like just to make it very simple for you, let's say here you have a clock signal. So it is like kind of enable signal, or it's a kind of, it serves as start signal, right? Start signal for the fetch stage and the execute stage, right? So let's say your clock signal looks like this, right? So this is clock signal, right? So both of them are connected to the same clock, definitely, right? So if we say that when, so you are providing this clock signal, and we say that whenever our rising edge arrives, rising edge mean that the value is changing from logical 0 to logical 1, then the next instruction is fetched, right? So what will happen on the first clock? The first instruction will be, I am here writing the instruction which is being fetched, right? Uh, Instruction 1 will be fetched in the first clock, right? So in the second clock, let me write, it's kind of like difficult to explain. Not to explain, but kind of difficult to represent. So at clock 1, instruction will end, sorry, let me go back. Yeah, from start. So see, so you have first clock and instruction 1 is fetched, right? In the second clock, what happens? Instruction 1 enters the execute stage here. It enters the execute stage. Let me write it here. It enters the execute stage, right? And instruction 2, it enters the fetch stage on the second clock, right? So whenever clock rises, it's basically mean that now the new input is taken, right? On the next clock, what will happen? Here you have next clock. So on next rising edge, what will happen? Your instruction 1 will be retired, which basically mean that it completes its execution. And instruction 2 will move into the execute stage, right? While instruction 3 will enter the fetch stage here, right? I think all of you got the idea, right? Now the thing is, like how quickly an instruction moves from fetch stage into execute stage, it depends what is the time difference between two consecutive rising edges, right? It depends, again, for example, how quickly instruction 2 moves from fetch stage to the execute stage. It depends upon the distance between two consecutive rising edges, right? So as you increase the frequency, this distance decreases, right? So for example, if I draw the same clock signal but with doubling the frequency, so it will look like something like this. And so in the same period where you earlier you were having, for example, in this time period, here you were having only one clock, right? But now in the same time period, I have now two rising edges, right? 1 and 2. So it's mean that I have doubled the frequency. So if I have doubled the frequency, this time has reduced. The time between two consecutive rising edges has reduced, which means now my instruction can move from fetch stage to execute stage faster, right? So as I keep increasing the frequency, I can basically enable my instructions to execute faster because now they are moving faster through the pipeline, right? Because the rising edges are arriving faster, right? So this is one way to speed up the CPU to by increasing the clock frequency. So higher frequency mean higher speed. I mean, theoretically, like in very simplistic models. Uh, However, there are downsides. There is limitation of everything, right? So when you increase the frequency, what happens? Yeah, that your hardware it consumes more power, and it becomes heated. So then you need mechanism to cool down, and also you need to, if you are consuming more power, so it's mean that you are consuming more electricity, which means you need to pay more, right? So other than that, other than like power consumption and heat, there are also hardware limits of increasing the clock frequency. So which basically mean that you cannot increase the clock frequency to infinity. When you keep doubling the frequency every time, like for example, just like as in the figure I showed you, like from this one to this one, we double the clock frequency. If I double it even on top of this as compared to this signal, so I am like I increasing the frequency, but there is a limit, right? And why there is a limit? Because uh, when you have very high frequency, you reach the physical limits of transistors, the physical limit at which the electrons can quickly move through the channels of the transistor. And now I don't want to go like this is not a lecture or course on the device on the physics of devices, right? Devices basically mean transistors, right? So I'm not going in that direction, but it means like if you very quickly, you switch them, which mean you have very high frequency. So what happens that your transistors will not work reliably. So when you will be expecting zero, basically, maybe you will not get zero, you will get one. Okay. So that is one, and that is a hardware limit. But I mean, at this basic level course, we don't need to worry about too much details here. The other, so like the first option is to increase the clock frequency. Yes, it will work for some like for a certain level of performance improvement, but then there are downsides like high power consumption and heat generation, and then there are also hardware limits beyond which we cannot increase the frequency. The other thing is like then what is the other way to speed up the CPU if we cannot increase the clock frequency anymore? We have reached the limit and we want to increase the performance beyond that. So what are the other options? The other option is to change the architecture. How we can change the architecture? There are various ways. We can do the architectural optimizations. So one form of that architectural optimization is pipelining, which we have just seen. So if you compare a processor which has pipelining with a processor which has no pipelining, which basically means it has a single stage pipeline, and you compare it with a two-stage pipeline. So two-stage pipeline will give you better performance. Now, if you compare four-stage pipeline with two-stage pipeline, the four-stage one will give you better performance and so on, right? But again, there is also a limitation to that one. And again, I'm not going to talk about that here. But uh, if you take a course on computer architecture in future, then maybe you will understand why pipelining starts giving you diminishing performance improvement as you keep increasing the number of stages. The other option is, so pipelining works well if you have a RISC processor. What is RISC? RISC basically stands for Reduced Instruction Set Computing. And why pipelining works well? So what is the like philosophy of RISC? Philosophy of RISC is like you have atomic instructions. Atomic instructions mean instructions which perform the operations which cannot be divided further into sub operations, right? So for example, you are saying move data from register R1 into register R2, right? So this is like an atomic operation in the sense that you cannot break down into any further sub operations, right? So if you have a program which is consisted of uh, instructions, all of which perform atomic operations, then it is easier to pipeline those operations, right? Which basically mean like you have, let's say if you have a pipeline here, and this pipeline, let's say, is consisted of four stages, right? And you have four instructions, and each one of them are performing atomic instructions, which cannot be further divided into sub operation, right? So it will be very easy for you to pipeline. Why? It will be easy because the instructions are simple, and since they are simple, they can be easily and quickly decoded. The hardware to decode them will be simple, and the time taken to decode them and to execute them will be uh, smaller, right? So those instructions will move quickly through the pipeline. Like if let's say if this is the exit point of the pipeline and this is entry point, so you will have one, two, three, four, and more instructions coming from this side, right? Okay. So the philosophy of RISC is to have instructions which are simple, atomic, and not be further divided into sub operations. Uh, and this basically RISC stands for reduced instruction set, as I said. So RISC, in comparison or in contrast to RISC, we have CISC. CISC stands for complex instruction set computer, right? So I will explain and you will then understand like why we are naming it as complex, right? So in this design approach, the CPU, which is designed using CISC approach, supports as many instructions as possible. On the other hand, the disk processor, they support fewer number of instructions. Like when we say support, basically it's mean that CISC has larger number of instructions which can be directly executed by hardware, right? Uh, for example, you have seen instructions in our previous lecture where we were saying, okay, load the data from the memory, data memory into register R1, and then we are saying move that data from R1 into another memory location. Everyone is with me, or everyone, I guess, recalls that example, right? So we were like not directly moving the data from one memory location into another memory location. We are saying, okay, read the data from memory location X, put it in register R1, and then move the data from R1 into memory location Y, right? So here we were using two different instructions. So this is approach of, like, you can say it is approach of RISC. In comparison to this, if you have a processor which supports directly moving data from one memory location to another, so where which says that you have, which gives you an instruction which allows you to read data from memory location X and write it into the memory location Y, right? So this instruction is more powerful in the sense it can do more work, right, in a single instruction. However, designing the hardware which actually allows the execution of that instruction will be more complex, and it will may take more time to execute that instruction as compared to an instruction which only first reads the data from one memory location and loads into the register, right? That instruction, designing hardware for that instruction will be relatively easier, and it will also take less time. And since now, if you have two different instructions doing the same thing, you can overlap their execution by putting them into two different stages of this pipeline. Am I getting like uh how to say, is it like becoming difficult for you to understand? If yes, let me know. And I think we have example in the upcoming slide. If it doesn't become clear after the example, let me know and I will try to explain on OneNote. Okay. So in RISC processors, the programs they use instructions. They combine instructions to complete complex tasks because we don't have more powerful. Just like I gave you an example. In CISC processor, you can possibly have an instruction which directly moves the data from one memory, single instruction which moves the data from one memory location to another memory location. But in RISC, for example, our ATmega328P, you don't have that kind of instruction. So what you do, you combine two instructions together, which is load data LDS, load data from one memory location to register R1, and then STS, which is store the data from register R1 into another memory location Y. Okay. So you are necessarily doing the same thing. You are achieving the same impact or same effect, but by using more number of instructions. So there are some features which are common or which you can find typically across RISC architecture or RISC processors. So what are those features? First, RISC instructions are fixed in size, and it simplifies instruction decoder. As a result of the implication of having that fixed size is that it becomes easier to design a decoder. The design of the decoder is simple, it's not complex. For example, in the AVR microcontrollers, including ATmega328P, all the instructions are uh, either 2 byte long or 4 byte long, right? There are even processors which have like fixed, all the instructions are, let's say, 16 bit long, which means 2 bytes long, right? So why does it help? Let's say let me try to give you an example. Let me connect OneNote and then uh, I will explain it. Okay, let me stop sharing so that I can share my desktop and you can see OneNote, right? And let me create new section. So week 4, day 1, and change the title of the page to page 1, right? Okay. So we said like RISC architectures, they have fixed size instructions and which basically help in having easier simpler decoder, right? Not only decoder, also other stages of the pipeline. But let's just focus on decoder, right? So let's say you have a processor where or a microcontroller where all the instructions are, let's say I'm keeping it simple, only 1 byte. So you have 8 bits, 0 to 7, right? And and let's say 0, 1, 2, 3, 4, 5, 6, 7. Let me put one more block here, right? And now let's say that uh, first 4 bytes, first 4 bits, they are always four most significant bits. They are always reserved for opcode. Remember what was opcode? It describes the operation which need to be performed by the instruction. So let's say the instruction has like a value of code in binary form as 0, 1, 1, 0, 1, 0, 1, 1, right? So how the instruction will be decoded then? The decoder hardware will, what it will do is like it will look at the first most significant bit of the instruction, and then depending upon the opcode it will decide what kind of operation need to be performed, right? Let's say 110 mean do addition, right? Right now what the decoder will do, all the every time decoder knows whenever I need to decode an instruction, I will directly go and look at the four most significant bits, and then based on the value of the bits I will decide what operation need to be performed, right? So if all instructions like add has 8-bit code, sub has 8-bit code, multiply has 8-bit code, and has 8-bit code, all the instructions, right? All of them have 8-bit code, then what will happen? All the time our decoder will looking at the first 4 bits. Now if I say no, a- add is 8-bit, sub is 8-bit, multiply is 16-bit, and is 32-bit, right? So then for some instructions, maybe the opcode is in four most significant bits, right? Four most significant bits. And for multiply, maybe then it is 8 most significant bits. And for and, maybe these are like 10 most significant bits. So decoder then, it is not like same thing all the time. Like depending upon instruction, decoder will need to know depending upon the instruction size. The decoder will need to look at different bits, right? Which mean that now since it's mean that decoder will need to first look at the size of the instruction and then decide which instructions, which bits need to be decoded to find the operation type, right? So it's mean our decoder is becoming now more complex, right? So this is the reason behind like if we have the fixed size instructions, how it will help in having a simpler decoder, right? And simpler mean faster. Okay. So having fixed size instructions simplifies the decoder. For example, in as I said, in AVR microcontroller, all instructions are either like they have a size of 2 bytes or 4 bytes. There is not much variation. Okay. CISC and CISC processors, they have instructions which are variable in size, like for example, in AT51, which is an example of the CISC architecture. So you have an instruction clear C, which has the code of 1 byte. Add has instruction has code of 2 bytes. Jump has instruction of 3 bytes, right? And maybe there will be some other instructions which will be even longer, right? So it's mean like decoder will be more complex. Any questions, confusion, comments? I know we don't have exercises or examples today because we are not doing assembly. So when we move to the assembly slides, hopefully you will have exercises. Another feature of the RISC architecture is that, as I said, it supports fewer number of instructions at hardware level. So the advantage of this is that definitely, if like for example, you are saying I am designing a processor which supports only two instruction, addition and subtraction, right? So and then you compare with another processor which supports addition, subtraction, multiplication and division. Now, the second processor, which supports four different instructions, it's mean that it is more complex because it also need to take care of multiplication and division, right? So it's mean that it will take more transistors, right? As compared to the one which supports fewer instructions. Now, remember, even if the processor A which supports only addition and subtraction, it doesn't support multiplication at the hardware level. You know that you can achieve the multiplication by repeated addition. For example, 2 times 3 is what? You simply add 3 two times, right? So 3 plus 3 is same as 2 times 3, right? So even if you're at hardware level, your processor doesn't support, you can run a program which says, okay, add 3 to itself two times. So 0 plus 3 and then 3 plus 3. So you get the same answer, right? But your hardware will be not complex and it will be using fewer transistors. However, assembly program will become more difficult. Just like I gave you an example, you will be using two add instructions to get the result of 2 times 3. And if you compare it with the CISC, you will be saying simply you will using one instruction, multiply 2 and 3, right? So your assembly program will be relatively easier. And if your assembly program is more like bigger in size, it's mean you will need more memory to store your program, right? Bigger mean more instructions. More instructions mean you need more memory to store those instructions. Feature 3, RISC architecture have limited addressing mode. Now you will ask what is addressing mode, right? So addressing mode is basically the way or mechanism to specify the operands of an instructions, right? So for example, when you say instruction add, right? Add uh, R1, R2, right? So here you are saying add the content of R1 and R2. So how you are specifying the operands? You are specifying the operands through registers R1 and R2. So this is known as register addressing mode. So this is like one mechanism, one way of specifying the operands. But there can be other ways, right? For example, when you say LDS, right? Uh, no, not LDS will not be a good example because here you will be loading the data into a register. Or okay, maybe I can simply like try to explain to what I mean by address. So here when here you specify some address X. So basically what you are saying move the data from some location in R1. And where is that data? That data is in memory, right? So this is again another addressing mode. So different like mechanism of specifying where the operands are, the operands which will be operated on by the instruction, right? So in RISC architecture, you have limited number of addressing modes, right? Uh, and as a result, so you will the advantage is that your hardware is not that much complex as compared to the case where you support more fancy or complex addressing modes. For example, if you let's say you are writing a program which is working on an array, right? An array of data, right? So what can you do? Let's say this is your base address. Base address means starting address X, right? And then you have index 0, 1, 2, and so on. So how you can iterate over the elements of the array? You have the address X plus offset. I'm just writing OF to indicate offset, right? So offset is 0, then 1, then 2, and that's the way, right? Now, how you will make the address of this location? By adding offset in the base. So what you will do, you will put this base in one register and you will put offset in another register, right? So this is another, and then you combine them together to find the total address, the address of the location, right? But there are like instructions which actually you only specify X and offset. You don't do the addition. The hardware is responsible for doing the addition and calculating the resulting address and use it, right? Use that address. But then it becomes more complex. Okay. So in RISC architecture, you have, for example, if you don't have this addressing mode, which allows you to iterate our elements of an array, so then it's mean you are limited in the flexibility. Yes, your hardware is less complex, but your program will become more tedious. Why? Because if if you cannot give these two different base address and offset at the same time to an instruction, so what you need to do, first you will have an instruction which will load X in a register, which will load offset in another register, then add them together, then whatever is the result, use that result as an address, and then read the data from that address. So your program will become more lengthy or tedious. Is everyone clear on this? Okay. Another feature of RISC architecture is that they are load store architecture. What does it mean by load store architecture? Load store architecture mean those architectures which, as I said earlier, which do not allow to move data from one memory location to another memory location in a single instruction. So there is no single instruction which can directly move the data from one location to another. So for that, if you want to do that, so first you need to load the data from memory into a register and then store it from the register into the other memory location other location in the memory, right? So here is an example. So here, for example, you are first saying uh, load data from this address into register R20, load data from the address 220 into register R21, add them together, and then write the result back into another memory location 230, right? So this is known as load store. In contrast to it, you can have uh, a CISC processor which doesn't follow this load store restriction. So it can do something like this. Let me write on, or maybe I can try to write here uh, instead of like going to one node. So it can do something like this. Add R20 and then uh, memory location. Let's say this is just a syntax, okay? 0x to 0. So it means what? It's mean read the data from this memory location 0x20, add it to the content of R20, put the result back in R20. Okay. So R so this is like uh, you are directly reading the data from memory and using it in an operation or an instruction without first placing it in a different register. Okay. In RISC architecture or in ATmega 328P, you cannot do this. So you first need to load the data, let's say in register R21, and then add them together, R21 and R20. Okay. So you always first have to load data into a separate register and then use it. You cannot directly use in an operation like add. Okay. Mm, yeah. The next feature about RISC architecture is that they follow the Harvard architecture principle, which means we talked about it in a previous slide. So Harvard architecture means that you have separate buses for opcodes and operands. What is opcode? Opcode is like your program or operation, and operands is data, right? So you have a separate code memory and you have a separate data memory, and you have CPU connected with both of them using separate set of buses, control bus, data bus, and address bus. So the advantage is that opcodes and operands. So here basically maybe it is a bit confusing to say opcode. So it should be like instructions. So the instruction is that the advantage is that instructions and data, they can go in and out of the CPU together. So for example, let's say you are reading first instruction, right? Remember, if we are using, let's say our CPU is pipelined, right? So when you when you fetch the first instruction, you will use the code memory. In the next cycle, fetch instruction is in decode stage. When it is in decode stage and the second instruction is in the fetch stage, so if the second instruction is in fetch stage, the second instruction is fetched from the code memory into the pipeline. And in the decode stage, let's say execute stage, you need to read the data from memory, so that data will be read from memory into the CPU. So which basically mean that you can read the content from two memories at the same time. You don't need to like how to say multiplex the buses between the two memories, bus between the two memories. So that is the good thing. But the disadvantage of this Harvard architecture is that it leads to more cost in general purpose computers. I think I explained it earlier, but let me state it again. So for example, in your ATmega 328P, all of these components are on the same chip. So on the same chip, you have a processor, you have code memory, you have data memory. So the bus is also on the chip, right? So, but in general purpose processors, that is not the case. In general purpose processors, you have a separate chip for code memory, separate chip for data memory, and a separate chip for the processor, right? So if that is the case, it's mean that your buses, they are crossing the chip boundary. Like for example, this control bus, it is connecting the CPU chip and the data memory, right? So whenever the buses or the data, they cross the chip boundary, the flow of the data becomes super slow, because the signals, the speed at which the signals travel across the chips is much slower as compared to the signals or how the data flows within the chip, right? So not on so it makes the data movement slower. Not only that, it also make the design costlier. Why? Because uh, it's mean that here you have three set of pins or three buses crossing the CPU, and three more set of lines or three buses crossing the CPU. So in total in total you have six different buses, right? So which means you will have more pins, and more pins you have, it's mean your CPU becomes more expensive, right? Because it not only increases its size, it's also increases how much amount is spent in designing that processor. So it's better to have lower pin count. Okay. So that's why the Harvard architecture is expensive in general purpose computers. And if everything is on the same chip, it doesn't matter, because yes, they are crossing different modules and components on the same chip. Oh, okay, let me discard all of these markings. Okay, so here is an example. Uh, so you have the instructions LDS, load data from static memory from address 0x10 into R20, and then you are saying add R21 into R20, right? So the first instruction will be fetched. In the next cycle, the first instruction will go to the execute stage, second instruction into the fetch state, and after like another cycle, so in total in three cycles, the two instructions will be executed. So the point here to highlight is that when this first instruction is you are executing the first instruction, first instruction in purple color, it is an execute stage. So it is reading the data, right? It is reading the data from which address? from this address of the data memory, right? And at the same time, the add instruction, which is in the fetch stage, this instruction itself is moved into the CPU from code memory, right? So this purple instruction, LDS, it is reading the data from the address of the data memory at 0x10 into the register R20, and at the same time, this instruction itself is moved from code memory uh, into a register which we haven't talked about, but typically they have a register which is named as instruction register, which holds the instruction copied from the code memory into the CPU. Okay, so both successes are performed at the same time. Any questions? Okay. The next feature about RISC architecture is that more than 90% of instructions are executed in a single machine cycle. Why? Because unlike CISC, RISC architecture does not employ micro-ops. I will explain what is micro-op and why having not micro-ops help RISC architecture to execute most of the instructions in a single machine cycle, right? So let me first get done with this slide and then I will come back to this point, okay? So in CISC, a complex instruction is broken down into smaller atomic instructions named micro-ops. So what is micro-op? Micro-op is a smaller atomic instruction, an operation which cannot be divided further. Okay. So, and why we do so? Why we divide a complex instruction into smaller atomic operations? Because complex instructions are hard to decode quickly and in parallel. So, as I said earlier, so anything which is complex, it takes more time to execute it. And micro ops are more suitable for pipelining, less variation relatively in execution time. So here is an example. Okay, and not all instructions need to be broken down into micro ops. So here is an example. Let's say you have instruction increment the content of the register EAX. It is known as extended register A. Okay. So this is actually a register in Intel microprocessors. Okay, name of a register. So here we are saying increment the content of this register. So this instruction, what operation it is performing? It is simply doing this: add 1 to the content of EAX, right? And who will do this? ALU will do this addition, right? Arithmetic logic unit. Now we cannot break down this instruction increment EAX into further into more sub operations. It's not possible, right? Because it is kind of atomic. So that's why we are saying not all instructions in the CISC processors need to be broken down into micro-ops because they cannot be broken down, right? However, some instructions are complex and they can be broken down into micro-ops. So here is an example. Add mem EAX. So mem we are putting in bracket. So we are saying add the content of register EAX with the content of a memory location whose address is this one mem, right? Add and then put the result back in the memory, right? So if let's say the address is X, so you are basically saying this is memory, right? So go to the in this single instruction, what you want to do, go to the address X, read the value, whatever value, let's say it is 10, add it to the content of EAX, let the content of EX, let's say is 5. So 10 plus 5 is 15. And then after the execution of the same instruction, the result should be placed back at the address X. So it should become 15, right? So this instruction can be broken down into micro ops or sub operations, right? So what are those micro ops? First, we can say, okay, first micro op is our first sub operation is loading the data from that memory address X into a temporary register in some register, let's say R1 or something, right? So you are simply loading the value of X, which is let's say 10, and you are putting it in a register which we are naming as 10. Then you are saying add the content of the temp register with the content of EAX. So here you are now doing 10 plus 5, right? And then in next a micro op, you are saying write the result which is available in temp in the memory location specified by the address mem or x in our case. So which is basically you are saying write back the result 15 into the memory location, right? So we have broken down one instruction into three micro ops, right? So remember what is now advantage? The advantage is what is advantage of breaking down into three micro ops? So if you have a pipeline, right? So let's say you have a pipeline with uh, I don't know, maybe four stages, right? So I'm simply naming as micro op 1. I'm naming it as M1, M2, M3, right? And let's say this pipeline, our instructions flow in this direction. So when M1 is in this stage, M2 will be in this stage, M3 will be in this stage, right? So you are basically overlapping the execution of the sub operations or micro op by putting them in different stages of the same pipeline, right? And compare it to the case where where you are unable to break it. Now, what will happen? That you will have this add instruction. This instruction, let me name it as I. This will be one instruction, and if you say we cannot pipeline it, we cannot break down it into the further stages. So let's say it is in the stage. Uh, there is some other instruction X in front of it and instruction Y and behind it. So since now I is doing a lot of work, like it is first reading the data from memory, then adding it, then writing the data memory, then it will take more time. It will stay in this stage for longer time. It will occupy this stage for longer time, which means all the instructions behind I, they will be blocked as long as I is not done with this stage, right? So more complex the instruction is, more longer it will take or more longer it will stay in that stage. Okay, now maybe I can come back here. So more than 95% of instructions are executed in one machine cycle in RISC because unlike CISC, RISC architecture does not employ micro-ops. So now we've broke down this add instruction into three micro-ops, right? Now compare it with the case where you have no complex instruction. So most of the instructions, they are already like atomic instructions. So most of them will be like executed in a single cycle. But here we have divided this instruction into three micro-ops. So these three micro-ops together are representing one instruction, right? So if each micro op like takes one cycle in each stage, so it will take longer time for all three of them to leave the pipeline, right? So because all three of them are together representing one instruction, right? That's why in CISC architecture, execution of the instruction is slower as compared to execution of the instructions in the RISC because all instructions in RISC, most of the instructions in RISC, they are already in the atomic form. They are simple. Okay. Any questions? Okay. Uh, RISC architectures or RISC processors, they have at least 32 registers, right? So basically what we are saying here is that your CISC processors, they have relatively less number of general purpose registers as compared to RISC processors. For example, ATmega328P is an example of a RISC architecture and it has 32 general purpose registers. So more the number of general purpose register available, so it's mean that you can hold more data in registers. Holding more data in registers mean you are holding more data closer to the processor or CPU, right? Now, if 32 registers, it means like I can hold 32 data items closer to the processor, right? So if I have 30, I need to access the 33rd data item. So then what I will need to do? I will need to go down to the memory and bring it closer by placing it in the register. And since all the registers are occupied, I will need to like move one data item from one of those 32 registers back into the memory. So this like uh, moving the data out from the register into the memory, it will take more time, right? Now assume that I increase simply my general purpose register from 32 to 64. What will happen? I can hold 64 data items closer to the processor, right? So which means that it will decrease the more the number of general purpose register you have, lower is the need for stack and memory usages, right? So this is like a good thing about RISC architecture. Then other like CISC processors, they relatively have lower number of general purpose registers, like 8 or 16. Okay, any questions? Okay. Uh, okay, I think I don't want to start this new topic here. Why? Because if I explain these slides now, they are like tightly coupled what we are going to cover next here with branch instructions. So I want to cover them in the next, I want to cover it in the next lecture so that, when we are covering the branch instruction, the discussion of these flags is clear and fresh in your mind. Otherwise, I will have to again spend time on explaining them, right? So let me stop here. And if you have any questions, uh, please let me know. No questions? Okay. If no questions, I know our 2 days lecture was like kind of boring and less interactive as compared to our previous lectures. But that's fine. I mean, this was like because of the nature of the lecture. We didn't have any assembly instructions. So let me stop here. And if no questions, then that's all for now. And see you on Monday, Tuesday, Wednesday, on Wednesday. Okay. Have a nice rest of the day. You too. Have a good day. Thank you.